quadrature amplitude modulation, that is QAM, or quadrature amplitude shift keying. So the definition for QAM is a combination of amplitude and phase modulation scheme. If the amplitude and phase of the carrier is varied, the noise immunity is in the increased, such a system is called QAM. That is, in QAM, both amplitude and phase of the carrier signal are varied in accordance with the digital inputs of the signal. This is the definition for QAM. And the representation of the signal, that is SI of t is equal to root of 2 ES divided by TS into KI cos omega CT minus root of 2 ES divided by TS into Li of sin omega CT. Here ES is the symbol energy and TS is the symbol duration, and Ki and Li are the pair of constant chosen according to the location of a particular signal point. That is, two orthogonal carriers are used here, that is psi 1 of t and psi 2 of t. So psi 1 of t, that is equal to 2 divided by root of 2 divided by Ts into cos omega Ct, and psi 2 of t is equal to root of 2 divided by Ts into sin omega Ct. These are the two orthogonal carriers. Then by substituting the equation number 2 and 3 in equation number 1. So equation number 1, that is Si of t is equal to root of Es into Ki psi 1 of t minus root of Es Li into psi 2 of t. We can substitute the equation number 2 and 3 into a equation 1. We got equation number 4. The types of QAM, there are 5 types: 4 QAM, 8 QAM and 16 QAM, 32 and 64 QAM. In 4 QAM, there are 4 different symbols are available. Each symbol has 2 bits. In 8 QAM, 8 symbols are available, that is 8 different symbols has 3 bits. And in 16 QAM, 16 different symbols are available. Each symbol has 4 bits. And in 32 QAM, 32 different symbols are available. Each symbol have a 5 bits. Same as 64 QAM, 64 symbols are available. So 64 different symbols are available. Each symbol has 6 bits. So the generation of QAM, that is the binary data sequence, is applied into a serial to parallel converter. Then we have a output, the parallel outputs, that is example BK plus 1 and BK plus 2 and BK plus 3, like that. So this binary signals will applied into a DAC signal, that is digital to analog converter. The digital signals will convert it into an analog form. That is, the output of DAC is the odd bits and even bits will segregated into output of the DAC. So the odd signals is represented in B naught of t. The even signal will represented in output of DAC is B E of t. Then this B naught of t and B of t is applied into a multiplier. This is the message signal, and the carrier signal is applied into a multiplier is psi 1 of t and psi 2 of t. Then we have a output of the multiplier. We can add the both odd bits and even bits. So finally we have a S of t, the QAM output, quadrature amplitude modulation signal, present at the output of the generator. Then the 16 QAM consists of 16 symbols. Each symbol has 4 bits. The serial to parallel converter is used to convert the serial data into 4 successive parallel bits. B0, these bits are BK plus 1 are applied to a upper DAC, and BK plus 2 and BK plus 3 are applied at the lower bits of the DAC. The upper DAC have the input as BK and BK plus 1, and lower DAC BK plus 2 and BK plus 3. The output of the DAC are A naught of t and AC of t. These are multiplied with the respective carriers, that is psi 1 of t and psi 2 of t. The output of the adder is S of t, that is QAM signal. That is S of t is equal to A naught of t into root of Ps cos omega Ct plus AC of t into root Ps sin omega Ct. That is odd and even bit signals. Then the deduction, that is demodulation of QM, is the carrier recovery circuit here used as to recover the carrier from the received signal. So the received signal is multiplied with the carrier, then applied to a correlator. Then the parallel to serial converter is used to convert the parallel bits into a serial bits. This is the deduction circuit of QM. So here the carrier recovery circuit is used to generate the carrier, and the signal S of t, QM signal, is applied into a multiplier. Then we have a correlator. The output of the correlator is connected to a ADC. So ADC circuits will produce the analog signal into a digital signal. So finally we have a parallel to serial converter. So the parallel BK plus 1 BK plus 2 and BK plus 3 signal will convert it into a serial bits of stream, that is B of t, present at the output of parallel to serial converter. Then this is the consultation diagram for 4QM and 16QM and 8QM. The bandwidth of QM, that is equal to 2 divided by n into TB. So TB is a bits duration, so that will change into 1. TB is equal to 1 divided by FB, we can write. So the FB will goes into upper side. So 2 into FB divided by n is the bandwidth for QM. So finally the probability error, that is P, that is which is approximately equal to 2 into 1 minus 1 divided by root of m into the error function of root of EB by n naught. This is the probability error for the QAM.